Record. Okay. All right. So this one here, chapter 17, number 48, it says many artists sing very high notes in ad lib ornaments. And is that a cadenza? Yeah, I think that's how you pronounce it. Anyways, the highest note written for a singer in a published score was the F sharp above high C at 1,480 hertz. Wow. Okay, let's get to A here. Find the wavelength of this sound in air. Okay, so this is your standard velocity equals frequency times wavelength. Again, one of those properties we learned in general about waves in chapter 16. If we apply it to sound waves and to this one, we can just simply say, okay, the wavelength is velocity divided by the frequency. The sub part of this is they just said it is sound waves in air, and presumably at room temperature. Actually, I just realized I don't think we've done any that had some kind of variation in temperature. But 343 meters per second is the velocity of sound in air at room temperature. And then the frequency is the 1,480 hertz. And unit-wise, a hertz and a per second are the same thing. They cancel off, and so we're going to have an answer in meters. All right, so I'm grabbing my calculator. 343 divided by 1,480 is 0.232. So 232, about 23.2 centimeters, 232 meters. All right, so B, I have a feeling that that probably wasn't the hard one. Moving on here. Suppose people in the fourth row of seats hear this note at a sound level at 80 dB. Find the displacement amplitude of the sound wave. All right, so there's two ways to measure the volume of sound. One is called the intensity. That's the amount of power in a given area. And the other one is the sound level, which is a logarithmic scale, and there's some advantages to that. But the scale is a reference scale between the smallest amount that the human ear can hear. This is I naught, so the lowest intensity, and then this is what you're listening to, and this is what we would call the sound level, measured in decibels. So they say here we have 81 decibels. So it's 81 decibels, which means then I could calculate the intensity of it because the reference is the 10 to the minus 12. So good number to commit to memory. Just that and the 120 dB. So the 120 dBs for pain and the 0 dBs for threshold of hearing, or an intensity of 10 to the minus 12. Now, if I go to solve this, this would be 8.1 log of the intensity, 10 to the minus 12. The anti-log would make 10 to the 8.1. Then times 10 to the minus 12 would give me the intensity when I move that over. All right, so let's take 10 to a power of 8.1 and multiplied by 1 times 10 to the negative 12. And it looks like we've got an intensity of 1.26 times 10 to the negative 4 watts per square meter. So it's the sound level, the decibel level there, that allows us to figure out what the intensity is. And then a nice equation to commit to memory, or at least know where it is. It's an extension of what we did for string waves. In fact, I'll do string waves first. So back in chapter 16, if you're talking about the energy flowing down a string, of course, it's just one-dimensional, so you don't really talk about intensity. It doesn't, spread out and change. It just goes in a straight line. So So the power is 1/2, and the 4 factors aren't too much of a surprise because the energy should be dependent on, how much mass is moving, V for the velocity, how fast is it moving, the frequency, now it's actually angular frequency, and it is squared, and that might be a little bit of a surprise, but maybe not too much when you realize things like kinetic energy is velocity squared. So we can take that rate squared and just multiply by the velocity. And then it's the amplitude squared. Now, when we got over here into this chapter with sound waves, talking about the power wasn't as useful, although it can be. In fact, I'm thinking of a problem we did earlier today. They said that the power coming from this speaker system, it was a public address system, was 6 watts. We can talk about the power coming from it, but the thing is since it spreads out 3-dimensional and it kind of comes outward, it is better to talk about the intensity. And the power then can spread out over a bigger area, because ultimately for sound waves, it's how much goes into your listening device. Your listening device might be your ear, or the listening device might be a microphone, but it's how much then power in a unit of area, because your microphone or your ear is only so big. So intensity becomes more useful than power, because the total power is kind of irrelevant to how loud I hear. I only hear the energy that goes into my ear, not the stuff that goes up or down or left or right or back, but the only stuff that comes forward. So with that in mind, if we take what we learned in chapter 16 and divide both sides by area, this side of the equation becomes the intensity. And like I said, and I'm going to say again, and I think I even said it in the video lecture, that dealing with sound waves, the intensity is kind of at the heart of what we want to know, not the power. Of course, not 100% of the time, but most of the time it's the intensity. So if you divide this power by the area, you get intensity. And then you get over here, if this is the mass per length, then you divide by area, you get the mass per volume. And so this is the density of the air. And so we use a rho, so the density per volume. Okay. So we still call it density. I know that can be a little confusing, but what we mean is mass per volume as opposed to mass per length. Because we're talking about a very different type of wave. We're talking a wave that goes out in 3 dimensions as opposed to a string wave that goes in a straight line. So that's the result. But everything else stays the same: velocity, angular frequency. We also like to do one more thing it's worth mentioning. Since we like to use the symbol capital A for area, using it for amplitude is a potential confusing point. So we switch it to an S, max. S being the displacement of it, and so S max being the maximum displacement. Why S? I'm not really sure. I don't know if there's any value to be mentioned along there, but the real value is to switch away from the A. Otherwise, we have a capital A for amplitude and a capital A for area, and that's confusing. So that should be pointed out. So dealing with sound waves, we really want this. And that's where this question comes into play, because this question, we just figured out what the intensity is. And all these other things we know about the sound waves, and we're being asked for this number here, I believe. Let me come back. Find the displacement amplitude. Yeah, so we like to find that S. All right, so I'll call that page 1. All right, so moving on here into a page 2, the intensity, as we discovered, was 1.26 times 10 to the negative 4 watts per square meter. And now that I did all that talking, I kind of forgot how we got that. Oh yeah, they gave us the sound level. They gave us the 80 decibels. Okay. So then I can put in a 1/2. The density of air, look it up. Just Google it. It's also in this chapter. Of course, air pressure changes, so the density changes a little bit. Sometimes you have high pressure and low pressure. So it's about a 1.2 to a 1.3 kilograms per cubic meter. I'm just going to kind of pick the middle ground at 1.25 kilograms per cubic meter. Probably a little lower is a little better. That 1.25 might be like not to say today, but we probably have a lot of clouds, low pressure. Yeah, so it's probably lower than this density today. In fact, most days are probably below this. So maybe this is a hair on the high side.
Will that cause us to run into like any serious issues on exams? Which ones we choose, or not really?
No.
Okay, cool.
No. Yeah, which one you choose doesn't really matter. I'll be looking at and some. It's like the speed of sound, actually. Some people pick 343, some people go 340, for 340 even because they want two significant figures. Some go 344. Some go 345 because it's a multiple of 5. Yeah, I think 344 is probably the best, but 1 meter per second certainly doesn't change the answer by much. And a given room could be a little warm or a little cold, so it's certainly justified also. All right, but I'm gonna go with 125, and we'll look at the answer in a minute here. See what they pick. Wouldn't surprise me if they just do 120, go to two significant figures. The velocity, and there's what we brought it up again. 343 or 344 or 345 or just 340. All those are good as long as we're talking about air. I know there was a problem we did earlier where these were sound waves in water, and then definitely 343 would not be appropriate for sound waves in water. Okay, they were way up like 1500 for that one. Angular frequency. This would be the 2 pi, and let me come back to this. This would be the 1480 hertz, and so I'll square that. And then finally, we get the amplitude squared. They should put max, since that's how your book labels it. Okay, so let's see what I get here. And maybe I'll just do this side of the equation because I'm looking at this. I want to take care of this one first. 2 times pi times 1480 and square that. Multiply that by 343. Multiply that by 1.25. Multiply that by 0.1. So that's everything on this side of the equation. And so let me take the 1.26 times 10 to the negative 4 and divide it by that last answer. That would be s squared. And so finally, taking the square root, you will see. And one thing that's a little nice to see with sound waves here is how incredibly small we're talking about things. The movement of the molecules is incredibly small. The amount of energy is incredibly small. Sometimes, and students deal with conservation of energy, like in collisions in 121, they go, hey, what about all the energy, including the energy of sound? And usually when we have two things collide, we just go, let's consider the kinetic energy, let's consider the heat energy, and we never talk about the sound energy. And it really takes this chapter for us to justify why sound energy is just incredibly small number. It's 8 decimal places down. So we just usually ignore the energy associated with sound when we're dealing with anything else because it's so small. Okay. So that's the displacement and in meters. And by the way, an atom with a diameter of about 10 to the minus 10. So, okay, so this does have quite a bit of movement. I mean, this is about 800 times the diameter of an atom. So in terms of the size of an atom, it moves quite a bit, but it's still a small number. And facts, I might jump over and look at their answer before I go on here. So this was 48. They got 8 point. Now they got 4 1 times 10 to the minus 8, but it might go back to this density. Let's see.
We also might have chosen like a different speed for uh, 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 speed of sound there.
Yeah, let me check them. Okay, so they did do the 343, but they did the 1.20. All right, so a couple of decimal places. So, anyways, but the logic is still there. So, and they did exactly the same formula and stuff. So, again, absolutely fine. If I saw that on the exam, I'd go, oh yeah, 100%, perfect. Yeah, nice. Okay. And then I think there was a C on this one. If I'm going to see, what if? In response to complaints, Stratus later transposed a note down to F above C, which has a frequency of only 1,397 hertz. Okay. By what increment did the wavelength change? Oh,
Did they want like a scalar for that? Like I didn't really get that.
yeah, I agree. The question's not real clear. It says increment. So we could say by how much length? We could say by how much percentage? Why don't I start with just how much length and see where we go? Because back in A, we got a wavelength, and so this is F sharp. I think it was F sharp. Is that right? F sharp above high C. Okay, so is high C the fifth octave? Any music lovers out there? Is this an F5 sharp? Well, it's an F sharp something. I don't know if it's a 5 or a 4. I want to say it's a 5, but nonetheless, I'm going to put that we calculated earlier that the wavelength was 0.232. Oh, good. And I'm glad I did 3 decimals because this is going to change, but not by much. Because he lowers it from an F sharp down to an F. Big deal, really. So let's get the wavelength for just F. And again, I think middle C is a C4. So the one high C would be C5, and this would be the F sharp above it. So this would be velocity divided by the frequency. The velocity is 343, and the frequency, now he drops it down to 1,397. All right, so what's the new wavelength? So 343 divided by 1,397, and we're looking at 0.246. So if I subtract the two, 6 from 2 is a 4, 4 from a 3 is a 1. And it looks like there's a change of about 1.4 centimeters. Well, that's more than I first gave it. I thought, from an F sharp to a F isn't much. But, all right, centimeter and a half, something like that. Okay. We could also do a percentage. We could say it changed by 0.014 out of 0.232 and then multiply by 100. So not sure how best to answer this. Although when it says increment, I'm thinking distance. That might be the part, but I'm going to go with a percentage too. See what the percentage change is. Question could be a little clearer if they said do a percentage change or something. So this is about a 6% change. Yeah. Again, more than my initial reaction was. Makes me think I did it wrong. But let's see what the author did. So he calculates the new wavelength and yeah, gets this number 0.246 and then says it changes by he does a 1.38 centimeters. Actually, he does a 13.8 millimeters. Okay. He does one more decimal, but and he just does the increment. He does the change in the wavelength. Okay. So there we go.
Awesome. Yeah, I got stuck on part B because I forgot to use the like other equation for intensity, and then the last one I was just confused by it. So thank you.
Yeah, why with part B is that one that we use? It's like delta P max equals S max over PV omega. That why is that not applicable in this scenario?
Oh, wait. Okay, before I answer that, let me just make sure I think I know what equation you're talking about. It has it says delta P, and then it has a rho, a V, an omega, and an S max, right?
Yeah.
Okay, good. The reason that's not applicable is this P right here is for pressure, not power.
Okay, gotcha.
So this is the connection between the displacement wave and the pressure wave.
Got it.
But this one right here is the connection between the displacement and intensity has power in it, not pressure. And I know they're both a capital P, so you might interpret, or simply put, we don't know this number. We can't use that equation.
Gotcha.
We do not know what the pressure is. We know what the power and the intensity is, but we don't know the pressure. But,
gotcha. So if we're given sort of, if we're given decibels, we can use decibels to sort of find intensity, and then we'll go this route with the I equals 1/2 rho V omega S max squared. If we're given pressure, we can go to that other equation.
Right. Right. Yeah. Good. Yeah. Good point. I didn't know if you were interpreting this as power or.
I'm not sure what I was interpreting, but I get it now.
Okay. Okay. All right. All right, nice one there. Okay, so that was Hunter's there. Now, if I remember in the chat, someone wanted me to look back at number 1 here on the review. And all right, I'll run through this one again. And for those of you, some of you saw this a first time, and we had that coordinate system. I'm gonna I'm debating if I should do the same. Do it from the center. Yeah, I'm gonna do it from the center. All right, so let's try this one again. Let's see, I better write down a time. What is this? 3:27. Practice test number 1. All right, well, and I'll begin here by kind of making a solid wall, putting a spring, putting the cylinder, connecting the spring to the axis, making the ground, and then do a free body diagram. Because the free body diagram, we want to look at all the forces. Now, turns out we're not going to really care about the vertical ones, but I'll include them. So pulling down is the force of gravity, mg. Pushing up, and it would actually make contact right here at the bottom, but I'll draw it kind of up here in my diagram, would be a normal force. Touching along the bottom also would be some friction. It does say it rolls without slippage, So it'd be a static friction. So I'll just put a F with a sub S. Okay. I'm going to put an arrowhead, kind of a double arrowhead, because as it goes back and forth, sometimes the friction is positive to the right and sometimes it is negative to the left. So I hope I can just kind of interpret that as one arrow or one line with a double arrowhead. I hope you don't interpret that as two forces. That's just my way of trying to say that I have a force of friction and sometimes it's positive and sometimes it's negative. Actually, most people, maybe I should do this. Most people, yeah, I think I will. Most people don't put a negative arrowhead. They just say, look, there's a force of friction. And if it's a negative number, then we have a negative of that arrowhead, which is that way. And so they're happy with a arrowhead just pointing to the right. That's kind of the universal way. So maybe I should do that in my free body diagram. Of course, and then the other thing is the force from the spring. And the spring, I'll just put a capital F and a sub S for spring. I hope I don't confuse static here with spring here, but I'll use a capital F and a lowercase f. And then that would be the force from the spring, which is minus kx. And I think that's everything. Force of gravity and everything touching us. We got the spring and we got the contact. So I like to split my paper in half when I have problems that, two things are going on at the same time. And in this case, I have a translational motion and a rotational motion. So applying Newton's second law for translation, as well as applying Newton's second law of rotation. And so I'll do the easier one. I think in our Physics 121, translational problems are easier. And let me just do the x direction. And so if I add up all the forces in the x direction, so from the spring, it's a minus kx. And from the static friction, it's an fs. And so that equals to ma. So that would be adding up all the forces in the x direction. It may or may not be obvious that we don't need the y. So I'll just put the y kind of out of the way. But if I add up the forces in the y direction, I get normal up, mg down. That has to equal to mass times acceleration in the y direction, which equals 0, which means the normal force is mg. So if we need the normal force for anything, that's what the y direction will give us. I don't think we do. That's why I kind of put it off here to the side. I think this is all just a horizontal forces and rotational problem. Let me pause on the translational one. Let me come over here and add up all the torques. Now, maybe up here, I'm going to put that the calculation for torque is RF sine phi. At least that's the magnitude of it. And then we can do the little right-hand rule from our mechanics chapter on rotation. I think that's chapter 10 in both the Survey and the OpenStax book. And so let's talk about the torque. The thing about torques, and one of the reasons it makes it harder, is you have to figure out the torque around what point. And I'm going to go ahead and pick the center. You could do the contact, and I noticed in the solutions that Don, the first time he did it, he did the contact point. Then he does it a second time in terms of energy. Then he does it a third time, and he does the center point. And for some reason, I like this center point, so I'm gonna go there. That's what I had done earlier today for a group. So I'm gonna do the center again. It doesn't matter. It comes out to be the same thing. But as I go to add up my torques, keeping this in mind, I'll look at all my forces. So there's the force of gravity, there's the normal force, there's the friction, and there's the spring. And so as I look at this, the spring is pushing right at the center. And remember, R is the distance from the pivot point, that'd be the center, to the force, which is also at the center. So the distance from the push of the force and the rotation is 0. So the spring doesn't give me any torque. Doesn't make it rotate. Now, the friction does. See, it's the friction that you push here, and it's the friction that tends to rotate it. So if I go to calculate the torque from the friction, the distance away, so here's the pivot point, and here's the distance to the force, would be capital R, the radius of this cylinder. The force would be the force of friction. The angle would be 90 degrees, because right there's the R, and then the frictional force is perpendicular to that. Now that's just the magnitude. Let me hold off on what I want to call positive and negative for just a second, because I just want to point out that the other two forces, the force of gravity is also right at the center, so R would be 0, so no torque from it. And the normal force would be acting down here. So in that case, R would not be 0, but the angle would be 180 degrees. The normal force would be going up, and the radius would be straight down, and the sine of 180 degrees is 0. So what I'm trying to say here is the only force that results in a non-zero torque is the force of friction. So when I go to add up all my torques, I don't want to say I've ignored the force of gravity or the normal force of the spring. I've included them. They just happen to be 0. Okay. So the only one that shows up in my equation is the force of friction. Okay. Now let's talk about plus or minus. Because this, I want to do a little different than I did last time. Last time I just picked the convention. The conventional pattern is if something rotates in a counterclockwise direction, we call the torque positive. And if something rotates in a clockwise direction, conventionally we call that negative. And if I were to pick that, but I'm not going to, I'm going to change it. This would be the equation. That'd be perfect. Because when the force of friction is this way, positive, that would make it rotate in a positive direction. Okay. So that would be good. However, here's what I don't like. And here's why I'm going to change it from the convention. You see, when this cylinder is moving to the right, so when the translational motion is positive, the cylinder would rotate clockwise, and traditionally we call that negative. And the reason I don't like that is because then when this acceleration on this side is positive, it would be corresponding to a negative over here, and they don't match signs. So because of that, I'm going to change from convention. So for this problem, I am going to call clockwise positive and counterclockwise negative. So now, when I say that my force of friction is positive, which makes it rotate counterclockwise, that would be a negative torque. So I use this formula for the magnitude of the torque. And that makes it rotate, when that friction is positive, that makes it rotate in a counterclockwise direction, which I'm going to call that a negative torque. I agreed. It is opposite of convention, but here's the advantage. The advantage is now a positive translational acceleration matches a positive angular acceleration. And a negative translational acceleration matches a negative. And I like that better. So again, when the wheel goes to the right, so this is positive, that would make the wheel rotate clockwise, which I'm going to call positive. So positive here goes with positive here. And likewise, when the wheel goes to the left. When the wheel goes to the left, the acceleration would be negative. Of course, that would make it rotate clockwise. And I am calling for this problem that a negative. So the negative here goes with the negative there. So now these have the same sign. So that's the part I like. The part I guess I don't like is I've got to break with tradition. And I've done this, so many more times with the traditional definition that reversing that is kind of hard. It's like, to the right, the x-axis is positive to the right. I'm used to that. Once in a while, I'll make the x-axis positive to my left. And when it does that, it's got to be for a good reason. So I think this is a good reason. So that would be my formula, if you will. Now, here's where the math comes together. Here's why I didn't think I would need the normal force. Usually you need the normal force when you've got to calculate the friction. And so here I can move the negative R over to there, and the sine of 90 is just 1. And I can use that and then use it over here for the translational motion. And I guess this should have been a capital M. There's only a capital M in this problem. Okay. And so this minus kx minus, and that minus comes from this one, so let's put an R down there. But then I've got this moment of inertia. And the moment of inertia is the moment of inertia of a cylinder. It's not expected that you remember that it's 1/2 mr squared. But it is expected that you could go back and look it up in chapter 10, either the Survey or the OpenStax book. That's what you did in Physics 121. So there's the moment of inertia of a cylinder. Another thing we did in chapter 10 was the mathematical connection between alpha and A. Maybe I'll put it up here, but A is equal to alpha times R. So I'm going to say alpha then would just be A over R. And you see when I do that, the 2 R's in the bottom cancel with the 2 at the top. And what I'm left with is this 1/2 MA. Now it has a negative sign, so when I bring it to the other, it becomes a positive. Now I already have an MA over here, so that there's 1 MA over on the right, and I'm going to bring over another half. So I will have 3/2 MA when I bring those together. Now, to get to the answer, I need to find the period. And to find the period, I need to get the omega. And to get the omega, I need to have an equation that looks second derivative of something equals, and it has a negative and a bunch of gobbledygook, which we would call omega squared, and then the x back again. And that's exactly what I have. If I bring the 2 over to here, the 3 and the m downstairs, I have the very important equation that chapter 15 centered around, which says anytime you take the second derivative of something and you end up with a negative, some constant, and that something, that same function back, the stuff out in front is omega squared. So this would tell me that omega squared is the 2, the k, and the 3m. And the period then is 2 pi over omega. So in this case, it would be 2 pi over the square root of 2k over 3m. So to finish the problem, I would then say it's 2 pi over the square root of 3m over 2k. Okay. And so there's the period. But got to do both translation and rotation, I guess, is what I'm after. And I think we have the solution worked out. Like I said 3 times, I'm going to go to the PDF. Yeah, so the first time Don does it, he calculates the torque as measured from the contact point. So he does it a little different, but he gets, of course, the same answer. Second time he does it with energy and then takes the derivative and gets the same answer. Then the last time he does it under what he calls alternative solutions, and it looks like he did it sideways on a paper, but he gets the same thing. So all 3 options are out there on the table, and you pick the one that you want to do. To me, this is the most straightforward one. I think the energy one is easier mathematically, but I don't think it's quite as obvious to do it that way. So this fits the pattern of chapter 15. So I forget who asked that, but that's a little interesting.
What problem was this?
So this was the problem from the test review.
Okay, that's what I thought. Thank you.
Yeah, so it's number 1 from the test review. And that's why I had those solutions. I think I sent out a bunch of information on the test review yesterday. I hope everybody got that.
Yeah.
Yeah, okay. And so that's the first one on the test review. All right, nice. Now I'm trying to figure out. Let me go to my other computer. I clicked something on my laptop. Oh, good. My camera's still sharing. What I messed up on, I'll lose it on my desktop. I wanted to jump back and see the chat. But that's okay. I guess I'll do the chat on my desktop here. I said that because whoever asked that, and I forgot who asked it so quickly that it didn't show up in the chat on my desktop. It was only on my laptop. So I logged in my laptop and did that one. But anyway, let me keep going. Because as I go to the chat here, it looks like, Anthony, you got the next one at chapter 18. A big number. Oh, I bet this is a hard one. Number 58. And let me write that down. Chapter 18, number 58. And I'll do a timestamp of, looks like 3:47-ish. All right. And let me scroll down here into chapter 18. Okay, keep going and find 58. What's 58? Oh, it's 58, this last one? Ah, yeah, it looks kind of long. All right, although it says a review problem, so maybe it's not so long. Maybe it's just a bunch of details. All right, so for the arrangement shown in the figure, the angle is 30 degrees. The inclined plane and a small pulley are frictionless. The string supports an object of mass capital M at the bottom of the plane. The string has a mass of lowercase m that is small compared to capital M. Now I'll pause there. That's a clue to tell me. And when I go to calculate the tension on the string, I don't need to worry about the weight of the string itself. I only need to worry about the big M, the mass. Okay. So that's kind of what I read there. It says the system is in equilibrium. Okay, so that again is helpful because that means the block, capital M, is not going up the incline or down the incline. And again, I think I'm going to have to calculate tension in here. And to do tension, I need to know acceleration. So acceleration is 0. It's in equilibrium. Okay. So the system is in equilibrium, and the vertical part of the string has the length h. Standing waves are then set up on the vertical section of the string. Find the tension. Okay, so A, I can see why they called this a review. Doesn't have anything to do with waves quite yet. The tension in the string comes around and is supporting this block of capital M. So if I did a free body diagram, and maybe I turn my paper here, you know, I'd feel better if I could figure out how to get that back. Okay, got it. Okay, so I can see here both going on. All right, so if I turned this and did a grid such that the y-axis is perpendicular to the incline, and put the mass here, and then called x-axis down the incline, then the tension is pulling up the incline, and gravity then, and this is the bad part of twisting the axis, this is the price we pay, but it's so worth it, is that gravity is actually then made up of a component along the x-axis and one perpendicular to it. So when I go to add up my forces in the x direction, which I would set equal to ma in the x direction, and I'm going to use that fancy word there, equilibrium. Okay, so that's not accelerating, so that's equal to 0. I can see that I have a tension pulling it in the negative x-axis, so I'll put negative. But I've got a component of gravity. So the force of gravity is mg. And if it's this angle here, it would be cosine of it. If I label it from this angle, it would be sine of it. And before I decide which angle to label, since they gave me this angle, let me choose the same one that matches here. Okay. So in other words, if I kind of redraw this incline like this, see, they're saying this angle here is theta. And then I tilted my axis so that this is the x-axis and perpendicular is the y-axis. And this then is the gravitational force. And I'm looking at this triangle. And so if I do a little geometry, this would be the vertical angle, that would be theta. So that would make this one 90 minus theta, and it would make this one theta. So So why don't I label this one from this angle down here, theta? So it would be opposite of theta. So it would be a sine theta. I could have just as easily said it would be cosine of 90 minus theta, which then, because 90 and its complement was sine, we would change it to a sine. So, and maybe I shouldn't spend too much time here because this is the review part of this review problem. This is the stuff that you learned in 121 about adding up all the forces. So that's the forces in the x direction, which means then I can just solve this for the tension. It would be mg sine of theta. Now I'm trying to remember. Did they give me numbers to work with? They did give me an angle. That's good. And g is 9.8. But they didn't give me an m. So I think you know the rules here. The rules are, if they give you numbers, put them in. If they don't give you numbers, they only give you symbols, then give the answer in the symbols that they have. I guess the only thing I would maybe say is this might be nice to put in at least the number of 30 degrees. Maybe not the 9.8. It's kind of debatable if I should put the 9.8. So I'll just put the sine of 30 degrees. And the other nice thing is sine of 30 degrees is 1/2. So 1/2 mg is the tension. So there's the part A. What's the tension? Okay. So as I said, this might be a long problem because it's number 58, but that was review. So maybe that wasn't too bad. But it looks like we go all the way to part H. So part B says, model the shape of the string as one leg and the hypotenuse of a right triangle. Find the whole length of the string. Oh. Okay, so they already told me this was H. And then maybe if I call the top part L, the whole length would actually be an H plus an L. Now, here's where some trigonometry or some remembering of geometry comes into play. I don't know if you remember your 30, 60, 90 degree triangles, but the hypotenuse and the short leg have a 2-to-1 ratio. That is, the hypotenuse is twice as long as the leg. That's probably what you learned in geometry. If you've forgotten that, well, let me just do this, that the sine of 30 degrees would be H over L. And the sine of 30 degrees, as we said a moment ago, is 1/2. So 2H is equal to L. So bringing that over to here, I actually have a total length of 3H. And again, I don't think they've given us any numbers for H. And so let me write the final answer in the symbols they've given me, which is the H. So the total length of the string is 3H. Okay. Model the shape of one leg of a hypotenuse. Okay. C, find the mass per unit length. Well, mu, the mass per unit length, is the total mass of the string, which they wrote as lowercase m, divided by its whole length, which would be 3H. Okay. So there's the mu, mass density, the mass per length. Find the mass per unit length of the string. D, find the speed of the waves on the string. All right. So velocity is the square root of the tension over the mass density. And earlier on, we got the tension to be 1/2 mg. That was this part A. Okay, 1/2 mg. And the mass density, I guess we just did that. That was the little m. So be careful with our m's because the tension is from the capital M and the mass density is from the lowercase m. And divided by 3h. If we simplify this mathematics, I would have an mg in the top and a 3h also in the top when I flip. The 2 would go downstairs with the m. And I don't think I can simplify anymore. And I can't really put any numbers in because they haven't given me capital M and lowercase m or h, but they gave me all of those as symbols in the problem. So I guess I'd say I'm done there. I've got my answer in terms of the symbols given. On to E here. E. Find the lowest frequency for the standing wave. Okay, well, frequency is velocity over wavelength. Let me leave the wavelength alone for just a moment, but the velocity we just did back in D, and we got the square root of mg3h over 2 little m, okay? This will give me a chance to kind of mention again what we did earlier today, is the fundamental frequency, is the lowest frequency. Find, let's see, did they say lowest? Find the lowest. Yeah, they said find the lowest. So the fundamental one. And so if I come back to my picture here, way back in A, it looks like it's tied down here. And then as it goes around the pulley, that would be a node. And so the fundamental one would represent a half wavelength on here. So we could say then that 1/2 a wavelength is h, or the wavelength is 2h. And then we can put that into here. So this would be a 2h. And then the square root of capital MG 3h over 2m. I suppose we could even do some simplification by moving this 2h into the square root. So when you do that, it has to be a 4h squared. So the 4 and the 2 would make an 8, and then an m, and the h squared would cancel with an h up there. So we would lose the h in the numerator and leave 1 in the denominator. And that 2 would be combined with that 4. I just want to double check. So I think that then would be a good answer for the frequency, because it's all in the symbols that were given, the capital M, the lowercase m, the h, yeah, and the g.
Where did you get the 1/2 lambda equal to h?
Now that, well, it's back to our picture on the fundamental. I drew it vertically, but I'm going to draw it for you kind of again like we did in our previous discussion. If I took a wall, tied a string to it, means the two ends are nodes. What patterns can I have? So for a standing wave pattern, I can have this. I could also have this. I could also have this. I could also have this. And so, like I was saying in the other sections, it's probably good to draw the first 4 and you begin to see the pattern. That is, this is this whole length, L, This is a half wavelength. This is 2 half wavelengths. This is 3 half wavelengths. This is 4 half wavelengths. And the fundamental one is this one right here. And so it's kind of hard to see, but that's actually half a wavelength. If you drew it out, it would continue on like that. That'd be one whole wavelength. So what I'm really saying is L, the length here, is half a wavelength. And for our problem, that's called H. L
Got
is
it.
H. So put an H. So 2H is equal to L. But it's one of these things that it's really easy once you see the picture, but there's no other way to do it than just to see the picture. And that's why right before the break, I went back and looked at it. It took me like 45 minutes to work out that problem for you when it could have and should have been done in 30 seconds if you already knew the pattern. But I tried to explain all those fundamental frequencies and draw all the patterns. And I started with the string, and then I went to an open pipe and then a closed pipe. And so all that was what this is. And so that's what makes chapter 18 and the standing wave patterns kind of challenging. And by the way, as a side note, that's why your author decided to put standing waves in a whole separate chapter, because this is just kind of hard to visualize. So the Survey book put the standing waves in chapter 18, whereas the OpenStax went ahead and mixed the standing waves together and the open and closed pipe together with the sound waves. And I got to admit, that's the appropriate place, but that's almost just giving the students too much in one chapter. So I kind of like the survey a little bit better on that, but I also kind of like the fact that there's only 3 chapters on waves instead of 4. So it's kind of the trade-off there. Okay, so let's see. So we are, this is E, find the lowest frequency. On to F, find the period of the standing wave having 3 nodes. Now, I'm glad you asked me to draw that picture, because as I look at the different patterns that can happen on this vertical section, I just did the fundamental one because that's what they said. What's the fundamental one? But the one that would have 3 nodes would be the first, I can use this word, the first overtone. That's the second harmonic, or the one that looked like this, one that has 2 humps in it. Because the 2 nodes would be where the string is tied. So coming back to the picture, that would be the bottom where the string is tied, and the top where it's under tension against the pulley. Okay. And then it would be a middle one. Maybe I'll change colors on here. So now I'm going to look at one that has this pattern in it. So a top node, a bottom node, and one in the middle. So there's my 3. But you see what that is saying, and I can only explain it by looking at the picture and say, isn't that saying that the wavelength is equal to H? So now I'm just going to repeat here in F that I did in E, and say the frequency equals V over lambda. And again, where V is mg3h over 2 little m. But now, instead of saying the wavelength is 2h, I'm going to say the wavelength is just h. Because we're not looking at the fundamental anymore. We're looking at the second harmonic, first overtone, 3 nodes, 2 half wavelength. All those are saying the same thing. So let me call it the second harmonic. And again, if we simplify this, the top, we have the M, G, and the 3 again. But when I bring the H into the square root, it becomes H squared. There's not a 4 this time, so we have a 2 down here. But there is the H squared. So one of the H's downstairs would cancel with one of the H's upstairs. And of course, that's the frequency. The period is what this one asked. And the period is the reciprocal of the frequency. Find the period. So I need to flip this and put a 2 little mh at the top and a capital M and a G and a 3 at the bottom. So there would be the period. I just better read that one again. Find the period of a standing wave having 3 nodes. Yep. All right, well, continuing on, it's a big one. Let's go to part G. Part G says, find the wavelength of the standing. Well, that's kind of boring. I did that. All right. Find the wavelength of the standing wave that has 3 nodes. Well, that's back to my picture. I'll mention it again. That's what I was trying to draw in green. If I drew one with 3, where's my green pen here? It would arch out, have a node in the middle, and go back. So there'd be a node at the top and the bottom and one in the middle. So there's my 3. And that would be a whole wavelength. And so the wavelength would just equal to H. I wonder why. Oh, you know, I could have, I see. I could have, I didn't. But I could have done F by another method. And it never got to the wavelength. So maybe that's why. But the way I did it, I actually found the wavelength already. So, all right, I'll just put wavelength equals to H. Okay, so there's G. F, G, what's next? H. And then H says, find the frequency of the beats. Oh, good. Something here talks about beats. Find the frequency of the beats resulting from the interference of the sound wave of the lowest frequency generated by the string and another sound wave that has a frequency that's 2% greater. Okay. So what's called the beat frequency is a result that when you have 2 different waves, maybe I'll do this one, another one that's maybe a little bit longer in wavelength, and therefore a little shorter in frequency. When you have 2 waves of different frequencies, there'll be times where they add up constructively, but then they'll slightly vary. So eventually they will be out of phase and they'll cancel each other. Then they'll get back to in phase and then they'll eventually get out of phase. So the sound would get loud, soft, and I hope you guys could hear that on the video lectures. I was doing it right there at the end. I remember kind of checking those videos before I sent them to you last Sunday, and I was, see myself hitting them and kind of counting, and I could kind of hear that whoa, 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 whoa sound, and it got louder, softer, louder, softer. So that's what the beat frequency is. It's the rate at which it gets louder, softer, louder, softer. And the way you calculate it is it's the difference between the two frequencies. So if I let maybe F1 represent the fundamental frequency, which I believe would bring us back to this E right here. See, this E said, what is the fundamental frequency? Let me read E again. Find the lowest frequency of the standing wave. Yeah. So if we did E right, this is the fundamental one. And you're asked to, and I guess I'll write it mathematically this way. I'll put F1 for the lowest, and one that's 2% greater. Well, 2% greater means this. It means, take the original and add 2% to it and multiply by that original. Because 2% would be 0.02 times F1. That's 2%. And since it's an increase, you're going to add it to the original. So the original times 0.02 plus 1, which is 1.02 F1. So this one is, this one they're asking you to beat, which is 2% greater, would then be this difference between them, which I guess really just comes out to be 0.02 F1. And F1 was what we got back in E. And so this would be 0.02 times the square root of mg3 over 8mh. Nice. Finally done. And this was a heck of a long one here. So let me turn to the answers here, scroll down to 58, and let's see how I did here. So for A, I got 1/2 of mg for the tension, good. For B, I got a total length of 3h, that matches. For C, I got a mass density of little m over 3h, good, that matches. For D, I got a velocity, that's the square root, and they got a 3 mgh capital M over 2 little m, okay, good. For E, they got the frequency is the square root, they got a 3 mg over 8 mh, okay, good. E for F, oh, that's interesting. The author actually does G first. Doesn't surprise me, remember, because I had to do G to get here. So the author does G first, and he gets a wavelength of H, good. Then he goes backwards here to F and gets the square root of 2mh, 3mg, good. And then the last one, he gets 0.02, although he writes it as 2 times 10 to the minus 2, okay, times the square root of 3gh over 8m. Yeah, good. All right, matched. So whoever asked this, I think this was Anthony. Was that you?
Yep. Thank you.
You bet. All right. So nice. Okay. Oh, Andrew, that must have been that practice one. Okay, good. You're welcome, Andrew. Okay, now let's go back to, take the next one on that list here is chapter 17, number 11. And I'll do a timestamp here of 418. Okay. And chapter 17, number 11, page 1. Okay, so let me scroll upward. That's because I'm in 18, and let's go all the way back here to number 11. All right, so number 11 says a sinusoidal wave is described by this displacement. Okay, maybe I better write that down. So they say S, and there's what we talked about earlier. They like to use S for displacement and stay away from that, using capital A for amplitude. But it looks like we've got 2, and I'm going to write it as 10 to the minus 6. They say 2 micrometers. They have cosine. Then they have the angular wave number as 15.7 inverse meters, units times x. Okay. Then minus, and then this would be the angular frequency, 858. And again, units would be inverse seconds multiplied by the time. And so no phase. A negative sign means it would be going to, well, you could actually say there would be a phase if you didn't use a sign, but anyways, but it's traveling to the right because of the negative sign. And so A here says, oh, hello. Did I freeze?
Yeah, I think you froze.
Okay. Well, I'm bummed that I'm froze, but also glad it only did that today or this time. You know, the first time. All right, so let me come back here. I'm going to put share here and see if I can reconnect. Spinning along. Nice. Seems to reconnect fine. Okay, good. All right. So looks like I'm back. All right. So let me read A here. It says, find the amplitude, the wavelength, and the speed. All right. So the amplitude, this is really kind of going back to, I guess it's really chapter 16, where we learned about the general wave equation. So amplitude, and let me spell it out, or at least abbreviate it as amplitude, because in this chapter, we thought using an S for the amplitude with a max is better so that we don't confuse it with area. So I'm going to put here amplitude, which is S max, would be the 2 times 10 to the minus 6. So that's an easy one. It's just standing out. Now the wavelength comes from the angular wave number. The angular wave number K is 2 pi over lambda. That's the number in front of the space variable, not the time variable, but the space variable. And so that's the 15.7. So if I grab a calculator, this would be a 2 and a pi, then divided by 15.7, giving me a wavelength of about circle these, 0.4 meters. Now, I believe the next one said speed. Okay, so to get speed, let me do angular frequency and frequency first, because the angular frequency is this 858. And that's the number in front of the time variable. Okay, so 858 divided by a 2 and also divided by a pi come out to be a frequency of 136.6 hertz. So to get the velocity, I would do wavelength times frequency. And so I already got frequency in my calculator. Let me then just go multiply by the wavelength of 0.4, and I get 54.6 meters per second. Nice. So I think that was the three parts of A, the amplitude, the wavelength, and the speed. Good. Now, B says, determine the instantaneous displacement from equilibrium of the elements of the air at a position x equals 0.05 and time equals to 3 milliseconds. Okay, well, that is exactly what this equation is. Maybe the point of the problem really is, do you recognize what they are giving you here? What they are giving you is the displacement. They're giving you the position as a function of space and time. And then they've given you the space where they want it and the time they want it. So it's really just kind of a plug and chug into here. Cosine, it would be 15.5. Now, I do want to be careful with my units just in case they played games on me, but no, it doesn't look like it. They gave me 15.5, and the units are inverse meters, and then they gave me distance in meters. Okay, I'll just put that straight in. And that means the inverse meters and the meters would cancel, and then I would just have a number, so a real number. So I better make sure my calculator is in radians. Then minus the 858, and that's in units of inverse seconds. So I better make sure my time is in seconds. So there is maybe the tricky part because they gave me in milliseconds. So let me write the time as 0.003 seconds so that the units would cancel and I'm just left with a number. And then, of course, I'm left with a number. That's my clue that this should be in radians. So I'm going to check the mode of my calculator. Yeah, I'm in degrees here. So let me change it to radians. And let me just take then the 15.7 and multiply it by the 0.05. Subtract off the 858 times 0.003. And it looks like I have a negative 1.789 for the argument of the cosine function. I'm in radians, so I'll just hit enter. That's a negative 0.216. Then I'll multiply it by the amplitude of 2 times 10 to the negative 6. And so this would be in a negative 4.33 times 10 to the negative 7. And I didn't put my units here, but that was meters because it originally gave them in micrometers. So I do see now there's quite a bit of unit stuff. So maybe that was the main thrust of this one is to watch your units. Now, of course, the other thing here is it says determine the maximum speed of an element in oscillation. This kind of takes us back to chapter 15. We had the maximum speed was the angular frequency, and I'm going to spell out amplitude, or at least AMP for amplitude, because in this case, then, the angular frequency is this 858, and the amplitude is the 2 times 10 to the negative 6. So if I multiply those together, 858 times 2 times 10 to the negative 6, I get a maximum speed of 0.00172 meters per second. Well, pretty slow, actually. And that was pretty small and negative. That bothers me in there. So I think that's all they asked. Let me check the solutions here. 17, let me scroll back to 11. Let's see, the first one they give micrometers, good. They give 40 centimeters, okay, good. They give a speed of 56.6, that's good. Oh, they do give a negative, and they give 0.433 micrometers, which would be the same. And then they give 1.72 millimeters per second, and that would be the same. Okay, good. So
Yeah, for some reason I wasn't I was just having trouble finding those formulas. I wasn't looking at chapter 16. I was so that was silly of me. I must have done too much physics today. My brain's giving up on me.
Well, yeah, that happens.
That makes
Especially,
perfect sense.
especially this late in the day.
Yeah.
Been doing physics all day. All right, let's cam back here. Actually, maybe our timed work out really well. I think looking pretty good. Let's see, what does this say? Andrew says, is there something missing in the last sentence of the review problem for number 2? Well, maybe. Let me check it out. It says that the string is oscillating in the 4th harmonic and has write an equation of motion. Oh.
I think you might have an email about this one, or there was some one that was cut off that I think you sent an email about.
Yeah, but that okay, that wasn't the review problem, so I think that was a little different. The one I did was cut, well, yeah, it was cut off. I forget what number. It was in chapter 17. But let me see if I can figure out what he's saying here by going to the practice. So it sounds like he's talking about the practice test here. Number 2. Well, yeah, I agree that maybe the wording isn't as good as it could be. But like the problem I just did, here's what it's asking. It's asking you to write this equation. And I know it's here about quitting time, but I'm going to just do this one real quick. And it looks like it's the last one in the chat room here. So if anybody has any strength left, I'll try to clarify this. But I don't know if the question's all bad. It basically is saying write the mathematical equation for it says the motion of the string.
I thought it was that equation you circled, but the answer has like a standing wave or something. So it says has a, and then there's like a blank. So I think it meant to say standing wave or something.
Oh, actually, no. I think it meant just to say motion, and you had to realize it was a standing wave.
Oh.
So I apologize for circling this one. This isn't really what I wanted to circle. This is a wave going to the right. This would be a pattern that would be to the right and to the left. So if you have something that looks like this, sine kx minus omega t, and you add it together with a sine of kx plus omega t. So the one we just did just had a wave which was traveling to the right. But what makes this problem a little bit harder is to recognize that you're going to get a standing wave pattern. So you wouldn't have this kind of math unless you started with the two added together. And I don't think for the test you have to actually work it out. But what this comes out to be when you do this, and let me just say they have an amplitude, if you will, but this comes out to be 2a. Then the cosine of the difference between them divided by 2. So when you subtract those two, you take that and minus this, you get a minus 2 omega 2 over 2. And then you get sine of the two added divided by 2. When you add these two, you get 2kx over 2. The 2's cancel off. The negative in a cosine function is irrelevant because it is an even function. And I think the way your book wrote it was to write the sine function first and then the cosine function. Okay.
I think I
Now,
got caught up on the part where you're supposed to recognize that it's standing. Like how would you recognize that? Just because the string is drawn as a flat line?
well, no, there's an endpoint to it. So the waves are going to go and then bounce off. So they're going to be they're going to be traveling in both directions. Yeah, I mean, if the string has an endpoint, it hits it and bounces back to you. And then it hits the other endpoint and bounces back. So basically, if the string is taunt on tie, it's both taunt and tied on both ends, you're going to get a standing wave pattern.
Oh, okay.
Yeah.
I just didn't think about that part.
Yeah. Okay. Good. So is the rest good, or should I keep going with this?
Yeah, if once I know it's a standing wave, I think I can get the rest. I got
Okay.
all the other values correct. Just
Oh,
get
good.
the final equation.
Yeah, good. And I'll just scroll down. So that's kind of the key there. Yeah, and then Don here does a good job with the solutions, but yeah, standing wave is the big one. Yeah. Yeah, that's the hard part, definitely.
Actually, I think I also am wondering how you would realize that to each, so from one node to the third node is a wavelength. That's always true, right?
From node to node. Oh yeah, I think you said it right. From the first to the third, yes, would be a wavelength. Yeah.
Okay.
Yeah. Which is fine. I would encourage you though, just say node to node is a half wavelength because we always deal with the half wavelengths.
Yeah, I think I drew the picture wrong actually.
Okay.
But I did put down that each node to each other is a half wavelength.
Good. All right, guys. Well, I don't see another question here in the chat, so let me say keep working on this. Tests on Tuesday. Have any more questions? I'll make video solutions. Send me your questions. We did some good ones today. I'll send these out to everybody, and I'll